Yeah, good afternoon, students. Today we are going to see the actual implementation of universal shift register with mode selection. So as we have discussed previously also that there are 4 different modes are there for the universal shift register. That is nothing but serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. These are the different 4 modes. Mode selection. With this 4 different mode selection, we'll discuss about the how to implement the universal shift register using Xilinx tool. We'll write the VHDL code. We'll simulate it using test bench. We'll synthesize it. After synthesis, we'll observe the RTL schematic and the technology schematic, and we will implement this universal shift register on FPGA, that is Spartan 3 XE3S 400. So as everyone knows that this universal shift register, it is nothing but it is a register which has both the right shift and the left shift with parallel load capabilities. Okay, so we can shift the bit either right side or on the left side with the parallel load capabilities, as well as this universal shift register, which is a combination of means it is a design of bidirectional shift register and or it is a unidirectional shift register with parallel load provision. Okay, so how this universal shift register will work? The main is nothing but depending upon your the mode selection. If we are going to choose that the input, we are going to send a data, that is especially we will choose the input data which is of 4-bit, that is by considering D as a serial input. So this serial input will shift the data towards right or towards left, and it will store the data within register. So it will shift the data either towards right or towards the left, and it will store the data within your register. So there is a need of your some clear pin is also required to you. Load pin is also required as an input pin. We require a clock pin also required to connect this different flip flops in a register. Okay. So always, as everyone knows that when the input pin is active low, then there will be a universal shifting of your data takes place. Okay, so when the pin is active low, that is nothing but either your load or your the clear. So when it is active low, then automatically your data will get shifted. So as I already discussed that 4 types of universal shift registers are there. One is your serial in, serial out shift register, in which the data is you are going to take it serially, input data you are going to take it, and you will get the output will also serially. That's why it is called as serial in, serial out shift register. Serial in, parallel out shift register, in which the data is we are going to input it serially 1 bit at a time, and output is you are getting it in parallel form. So similarly, opposite to this, in parallel in, serial out, data input you are going to take it parallelly, and outputting of your data takes place serially. And the last one is parallel in, parallel out shift register, wherein data is taken parallelly and the outputting of your data is again parallel. So here you are going to observe that especially how many number of clocks will required, or we can observe only 1 bit of your shift you are going to observe. Okay, so by selecting of your these different modes of your the shift registers. Okay, so let us you can see that here I will share my screen now. Is my screen is visible to everyone? Let me know. Yes, please. Anyone, please. Is my screen is visible?
Yes, ma'am.
Okay. So you have to choose this Xilinx software, that is Xilinx ISC's design suite. So once you click on this, So I'm going to tell you directly, we'll show you the code because the process flow is already explained to each and every one previously. Okay. So this is where the ISC project navigator will open, in which you have to implement your the project, right? So as per the previous, you have to just click on file, new project, and accordingly you give the different, we can say you have to select the FPGA device and all. So here I will just directly show you that this is your the VHDL code for your the universal shift register, which I explained previously. So in which first there is a library declaration, that is library IEEE, and then you are going to invoke the package of IEEE std logic 1164. Followed by there is a entity declaration for the universal shift register. There is a data input you are going to give through the port D. It is of std logic vector 3 down to 0, which is a 4-bit. Then clock is in std logic, which is a single bit. Then load is in std logic. Then clear is in std logic. Then M, which is used here for the mode selection. Out of this 4 mode selection, as everyone knows, there are 4 mode selections, so total number of selection bits will require 2. So that's why M in std logic vector 1 down to 0. Okay, and there is a Q out, which is nothing but outputting of your data. So it is of 4-bit. That's why it's a 3 down to 0. And then there is a end of your universal shift register. So in this way, you can declare here the entity. These are the different input ports, and this is your the output, which is nothing but Q is the output port. Now under the architecture, you can observe here under the architecture that you are going to use a process statement. So process statement itself, we can say a concurrent statement, but the statement you are going to use within the process are always executed sequentially. But here you can observe this is a process followed by the sensitivity list is with respect to the inputs, that is clock, M, which is a mode selection, load, and the clear. And here as you are going to perform some means just you are going to shift the data and you are going to store that data in a register. So that's why intermediate some variables are required to be declared. So here intermediate we are going to declare a temp and P, these two variables of each of 4-bit, and then you also declared here the C variable and initialize. This is just a counter type, it is going to act. So it will just measure the number of your the clock pulses. So that's why this variable C, we have declared it, its data type is integer, and we are assigned, it is a variable assignment. That's why we have considered the symbol as here colon and equal to. So all are able to see this? Let me know. Are you able to see this? Okay. So it is variable C. It is of integer colon equal to 0. So we have initialized its value is equal to 0. Then there is a begin. Then the first idle state is nothing but if your clear is equal to 1, then your output is Q is equal to assigned as all are 0. Else if clock tick event and clock is equal to 1, this is the attribute you are going to use, wherein you are going to check whether the rising edge of your clock is occurred or not. So once if this clock rising edge of your clock will occur, then it will increment this your counter, that is C is equal to C plus 1. Okay, so it will increment, and if C is equal to 2, then again it will C is equal to means between 0 and 1. Between 0 and 1 within 2 clock pulses it will perform its operation, otherwise C will again initialize to your 0. So like this you are going to set here the counter as a C to perform your shifting of your a bit, right? So here we are going to use a case statement for the mode selection and storing your the data. So for here you can see when 0 0, that is mode selection M is 0 0, so it will perform your parallel in parallel out operation. So when it is 0 0, so whatever the D input is there, that D input will send it to Q. So that it stands for, it will take input parallelly and it will send it a parallel output. So within 1 clock once rising edge of your clock will occur, within a 1 clock, this 4-bit data will be outputted on your the output signal, which is nothing but the Q, right? Now then followed by when 0 1 is there, then for the 0 1 it will perform serial in parallel out operation, wherein you are going to check what is the condition of your the load signal, because already we have set this clear to low. Clear is always low. When the clear is low, it will perform the shifting operation. Now we are going to perform the storing. So for this storing operation, then there is a need to check for the load, whether load is 1 or not. If the load is 1, then automatically this D input will be stored temporary into the your temp variable, and Q will be assigned as 0 0 0 0, means there will no any shift will be there. Else what it will happen, means else load is 0 as well as your we can say clear is 0, both load and clear is 0, then automatically it will shift and it will store the data. It will shift and store the data. So that's why here Q you will get it as, means it will perform the shifting operation. That's why LSB of your Q is temp of 0, because when load is equal to 1, we have stored temporarily this data into your temp. Now you are doing the shifting operation as well as simultaneously this and operation. What it tell you that it is a concatenation. So these are the first MSB bits, these three, and this is your LSB bit. Okay. So like this, you are going to shift and store it for serial in parallel out. Okay. So serial in parallel out. Serially in ho raha hai, that's why only one bit is going to shift that whatever the LSB bit which is there for the D of 0, now it will be a temp of 0 and it is going to assign to Q of 0. Okay. So in this way we can perform serial in parallel out operation, and again at the same time whatever may be the MSB bits of your temp is there, that we can shift it to your the LSBs, and it is again assigned to your temp. So that is equal to temp is colon and equal to, it is a variable assignment. MSB will be the 0 and this concatenated with previous temp of 3 down to 1. So in this way we can perform the serial in parallel out operation when mode selection bit is equal to 0 1, right? Then afterwards when mode selection bit is 1 0, it will perform serial in serial out operation. For this again it will check for the load. If load is 1, then it will initialize temp is equal to 0. Okay, and Q will be again initialized with all are 0, but the D input now we are storing it to the P. So why we are use temp and P differently? Because there may be a chances that depending upon the mode selection, we are using different intermediate signals. So if it is the serial in parallel out mode selection, we'll use the intermediate signal will be temp. Now if it is performing serial in serial out operation, so intermediate we are going to change it. So it is D is stored in a P, because during the same clock cycle it should perform the operation. That's why this intermediate signals we are chosen as temp and P different. Okay. So else what it will do, serial in serial out operation is there. So what it will do in this case, whatever the P of 0, which is an LSB BT will be there. Now it will be the MSB is there, because it is serial in serial out operation it is performing. Okay. So during the first clock, rising edge of clock, it will send this your the LSB bit to the temp as MSB, and temp of this 3 down to 1 will be the as it is. Then Q will be this, most MSB will be this as it is, and then it will take temp of 0. Means you are transferring a signal from D of 0 to P of 0, P of 0 to temp of 0, and temp of 0 to Q of 0. So in this way we are transferring the signal for serial into serial out. And otherwise what is the left operation is there? Now the left operation is parallel in serial out operation. Other it will perform parallel in serial out operation. Here for the parallel in serial out operation, it will check for the load is equal to 1, then it will initialize temp 0 and Q 0, because temp and Q both of them are used in the previous 2 stages. Okay. Now we have to initialize it to all zeros. Okay. It should means whatever it has stored the previous value, so it should make it to be a null one. That's why temp and Q is equal to 0 when it performs now parallel in serial out operation. Okay, so that's why else how it will perform parallel in serial out. So while performing parallel in serial out operation, at that time this temp will take the MSB as P of 0, and this that is this temp of your MSB bit, it is a parallel out is there. So that's why instead of, yeah, this is serial out, parallel in serial out. So that's why here the MSB bit of your temp is P of 0. Okay, so have you understood about this operation right now? Yes, students, are you there? Are you there? Students, let me know.
Yes, ma'am.
Okay, so here during your parallel in serial out operation, now this means we already said temp and q is equal to 0. So whatever the P of 0 is there, it will send it as an MSB for the temp, and this temp will be assigned to your q, means it is now going to perform your the right shift. Okay, so previously it is performing left shift, now it is performing the right shift. So in this way we are going to assign, and then P will be means again you can take the values of P as it is, where the concatenation means only the MSB bit we have taken here, so it will change only the MSB bit of your P. So like this we can perform all the 4 modes of operation, mode selection in the universal shift register. Now let us will go for check syntax. Here is the check syntax symbol is there. Under here you have to choose the radio button as implementation. For this implementation radio button, under the synthesize XST, here is the check syntax is there. So once you double click on this, the process will be running. Now it will check for the syntax, and the status will be observed here under the console window. Now you can observe in the console window, process check syntax completed successfully, means there is no any error is there. Okay, so if there is any error, it will show you the error. Suppose I will just remove here the semicolon on the line number 83, and I will save it, and I will go for the check syntax. Okay, so you can observe here in the console window automatically unexpected process expecting if. Above this line number 84, it is showing parse error unexpected and expecting semicolon. Okay, so here you are expecting that a semicolon, so that's why this is there. So again you can go for the check, save your program after modification, and again check for the syntax. So process check syntax completed successfully. So according to the line number, you can observe the error and means correct your the errors. Still you will get the check syntax completed successfully. So now your the check syntax is completed successfully. Now we'll go for the test bench. To go for the test bench, click on the simulation, this radio button. Okay, now once you click on the simulation on the radio button, you have to right click, say new source, and in a new source just say a VHDL test bench. While writing VHDL code, you have chosen VHDL module, but for the test bench you have to choose a VHDL test bench, and you can write here just X, Y, Z. Okay, then say next, 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 any name you can give. Now again you are able to see here this XYZ test bench has been created, but this auto generated test bench, you can observe here entity without port declaration is there. Again there is architecture is there, then there is a component declaration, it will take by default from your the previous entity declaration, which indicate all the ports including D, clock, load, clear, M, these are the input ports, Q is the output port, and then there are some signal declarations are there, and all these signal declarations are initialized with your 0 values, like D input is initialized with 0, clock is initialized with 0, load is initialized with 0, clear is initialized, M is initialized also with 0. Then intermediate signal, output signal Q is there, which is not initialized because it is an output signal. Then there is a clock period is there. For the clock period, it is mentioned that default timing is 10 nanosecond. Then under begin unit under test. So here is your mapping of your the port signals is done. So under this, under this mapping of your port signal, you can observe D with D, clock with clock, load with load, clear with clear, M with M, and Q with Q. So in this way, we can perform the port mapping here. Okay. Okay. So this is just a port mapping, or we can say like as this is your the component instantiation statement where you are doing the port mapping with the same signal, with the same signal. Now there is a clock process is there. Under the clock process, you can mention process begin clock is equal to 0, and here you just remove this wait for clock period by 2. You can remove it by wait for 10 nanosecond. Okay, wherever there is a clock period is there by 2, you can remove it and mention your the clock period as 10 nanosecond, because it is mentioned previously. You can mention it 20 nanosecond also, no problem, any value. Then there is a, this is end of your process. Okay, this is related with the clock, as this is a sequential circuit, so we need a clock signal here. So that's why there is a clock process is mentioned, wherein the clock is defined here. Clock is equal to 0 means it will be low for 10 nanosecond, again it will go high for 10 nanosecond, low high like this. Okay, then followed by there is a stimulus process, wherein this under this stimulus process, you have to add your the stimulus signal, in the sense input signal, that is load, clear, mode selection, and your D input. So all these inputs you have to add here under the stimulus process. So to save your time, I will just show you the test bench which is written previously. Okay, so this is your the test bench. You can observe in this test bench only I will show you the stimulus process. You can observe that this is the clock process. Under the stimulus process, so what is that? First, it is there is some wait for some time period. Here it is mentioned 100 nanosecond. Then you are going to enter your D input. Here I have entered the D input, which is 0110. As it is, as everyone knows, that D input is of 4-bit. So that's why you are entering it as 4-bit D input. Then there is a load input, active low. Then there is a clear input, active low for shifting and storing. Load and clear both should be active low. Okay, and then mode selection M is equal to 00. So what I will do now, I will just whatever the other process is there, I will just make it to be an comment one, and I will show you only this one, first process. What is that? Your first process, parallel in, parallel out operation. Now I have chosen a mode selection M is equal to 00. Then there is a wait for some time, and this wait indicates it is going to wait for an infinite time. Okay, so it is an wait for an end. Before end of your process, there is a need to wait for an infinite time. That's why it is a wait is there. And then end of your this, we can say a component. Okay, which is declared here. Okay, or we can say the end of your this architecture. Okay, so now what I will do, I will save my project right now. Here is the option is there, save. So once you save this one, now again you can go for behavioral check syntax. Okay, so it is showing that do you want to save the changes you made? Yes. Okay, so I'm not going to check for the XYZ, but I have chosen it the previous one. Now it is saying behavioral check syntax completed successfully. Okay, there is no any error in our the test bench code. If there is any error in the test bench code, you can rectify your error and again you can check for the syntax. Still you will get the, here on the console window you will get the comment as process behavioral check syntax completed successfully. Then you will go for simulate behavioral model. Now under this case you will observe how there is a parallel in parallel out operation is takes place. Now you will observe here in the waveform. Are you able to see the waveform, students? Yes, please let me know. Yes, student. Are you able to? Okay. Yeah. In this waveform, you can observe that there is a D input. We have set it to, in the test bench code, we have set it 0110. Clock is 0. Then load is 0. Clear is 0. Mode selection is 00. Means we'll perform parallel in parallel out operation. So what happens here? Parallel in parallel out, whatever the D input is there, it will assign to your Q. So you will observe here, you can observe this Q output is 0110. Are you able to see? And the time clock period is 100 picosecond. It is showing here. Okay. So in this way, you will observe that that you will get some output you will get the output here within this one clock period. Once the rising edge of your clock will occur, you will get the output here like this. Otherwise, in the previous initial stage, you will observe here that if there is more, means there is no any mode selection here set. So initially for the, as the rising edge of your clock is not occurred, so that's why Q output is, you are able to see it is U stands for uninitialized. And once the rising edge of your clock will occur, then automatically your output, you can see this clock is equal to 1, it is showing here. So once rising edge of your clock will occur, then it will send a D input to your Q output. So in this way, you have to simulate your code using test bench. Now only one mode selection I have shown here, that is parallel in, parallel out. Now let us, we will check for the second mode, which is nothing but serial in, parallel out. Okay. So whatever with the previously I had commented, now I will just uncomment it, all the lines. Okay. So under this first D input, I have set it, you can observe the changes. That's why I have set it now the D input. Previously it was 0110. Now I have set the D input to 0111. Load is equal to 0, clear is equal to 0. Okay. And M is equal to, I'm going to set it as 01. Okay. So I will set this M input to 01. Okay. So in this way, once your M input is 01, means it will perform now serial in, parallel out operation. Okay. So in serial in, parallel out operation, it is, you will be able to observe that only shift in your the bit, only one bit will get shifted. Okay. So I will just save this now, the changes in my test bench code, and again I will go for check syntax. Okay, in a process window, you have to click on this behavioral check syntax. Now it is showing behavioral check syntax completed successfully. Now you can click on simulate behavioral model. Now you can observe here that whatever maybe the MSB bit of your D input is there, which is shifted to your LSB. It is shifted to your LSB, and you can observe here that all the first 3 bits of your Q output, that is Q of 1, Q of 2 and Q of 3, all are 0, and this bit, that is D of 3 bit, is shifted to Q of 0. So in this way, we can perform with the mode selection 01, we can perform serial in, parallel out operation. So shifting of only 1 bit, but storing all the 4 bits at a time in a register. So clear? So in this way, it will perform the universal shift register operation. So like this, you can go and you can do the practice for the other mode selection, also with the change in your the different input bits. Okay, am I clear for students? This waveform is clear, which is a test bench waveform. Right? Now, similarly, I will close now this window. Now we'll go for here now we will go for the implementation, wherein for the implementation, first we have to, now we are done with the simulation. Now we will go for how the hardware is generated for this, the HDL code you have written for the universal shift register. So you can click on now synthesize XST. What is XST? Is inbuilt Xilinx synthesizer tool. XST stands for Xilinx synthesizer tool. So what is that? Once you double click on this, so you can observe on in a console window that process synthesize XST completed successfully, means synthesis is done for this code. Now you will observe that RTL schematic, that is register transfer logic level schematic. Click on this RTL schematic, it will ask you whether you are going to start with Explorer Wizard or start with schematic of the top level block. So I will start with the schematic of top level block and just say OK. So you will observe this is your the top level block of your universal shift register, wherein you can observe as per your port declaration D, M, clear, clock and load. These are the inputs. So you can observe these are the bus. That's why it is a bold and dark line is there. Okay, this is M input. This is clear. M is only 2 bit. Okay, M of 0 and M of 1. And this is the Q out. So this is the top level model. to see inside blocks of this, which is an RTL schematic. So you can just click on this. So you will observe this is your, what you are able to see. Here is a one mux is there, which is getting all these inputs and only one output, which is the temp output. Okay. So everyone knows temp and P, we have used the intermediate signal. Okay. So this is one. Now, as we go ahead, now there is a comparator, it is used here. Okay. So similarly, you will observe here that gates are there. Mux and gates are the basic components of your RTL schematic. Okay. Mux and gates are the basic components of your the. Okay. So you can observe like this different blocks. So this is your the mux. This again a mux, adder is there. So these are the different basic components of your RTL schematic. So if I will just, okay, you can observe right now the various mux, means it will just mapping of your this, the we can say the different digital blocks in the RTL schematic are especially mux, counters, adders, okay, and the different logical basic gates, right? So this is your the inbuilt model. Now if you double click on this any one of your mux block, you can observe this is the mux. This is the detailed diagram of that your the temp mux which is shown here. As you can replace your just 8:1 mux, you can write a code for the 8:1 mux and check it out. As per the expression, you are getting the gate along with the connections and all. Okay. So this is your the RTL schematic, that is register transfer logic schematic. Now we'll see the technology schematic, which is with respect to this, the device which we have chosen. So here we have chosen XC3S400, which is having a speed grade of -5, which is a standard speed grade, and having a package of PQ208. That is, it stands for 208 number of input output pins are available with this package of XC3S400. So now we will see the technology schematic. Now we have to start this, open this your technology schematic with the top level block. So the same top level block is there, same as that your RTL schematic. Only the remaining thing is that you will observe in the RTL schematic, you observe the gates and mux, but in case of your technology schematic, you can observe the lookup table. Okay, you can observe the lookup table and input and output buffer. Lookup table with XOR gate. The basic building block of your technology schematic is lookup table, but the basic building block of your RTL schematic is mux and the gates. But here in case of your the technology schematic, the basic building blocks are lookup tables. Now if I will minimize this, you will be able to see the whole circuit having a lookup tables and the mux and the XOR gates. Okay, so it will map your all this hardware into your the internal logic cells of your FPGA like this. Okay, so about this, is there any difficulty in the RTL schematic and the technology schematic? Yes, student, let me know. Is there any difficulty? Are you clear about this? What is RTL schematic and technology schematic? Now you can observe this the figure in the project which is stored. I will show you which will get you the .ngc and .ngd file. Okay, so our project name is Universal Shift Register. So this is the folder, it has been created here, wherein the software is installed in on an E drive. So automatically under the work library, it will store your, it will create your own folder, and here all the files related to your project are stored. So you can observe that this ngc, okay, which is nothing but your the we can say a technology schematic, and .ngr is your the RTL schematic. Okay, so like this, these two different files are generated here, right? So in this way, you can observe the different files which are generated under this your own folder. Now apart from this, you can write the implementation constraint file before translate, map, place and route. So how to write the implementation constraint file? To write your implementation constraint file, right click on your project name, say new source, and click on this your user constraint file. Okay, so you can click on this user constraint file. Yeah, I will just close this schematic. Oh, so just wait. Yeah. Now here I have to write the user constraint file. Using a user constraint file, we can perform the pin mapping. Pin mapping in the sense that we have to assign the out of 208 pins, we have to assign the pins to your the FPGA. That is D of, as you know that you define D, which is 3 down to 0. There is D0, D1, D2, D3. Okay. So these 4 bits we have to assign the pins. So just say new source. Here is the option is there, implementation constraint file, which stands for user constraint file. Now you can give the file name anything. So let's I will give uni underscore shift. Okay, uni underscore shift dot ucf will be created. That is implementation constraint file where we are going to perform the uh, your pin mapping, input output pin mapping, and just say finish. Now you will get it like this, a black window. So for this blank window in which you have to perform the pin assignment. So to perform the pin assignment, you know that there is a standard syntax is there wherein we have to write a pin mapping to D0, D1, D2, D3. For the inputs first initially I will do as per your the pin. So I will open the pin numbers for this. Students, you can just see the syntax for writing the user constraint file as net. Am I audible, students?
Yes, ma'am.
Okay. Yeah. So what is the syntax here? The net So we are going to assign here for the input switches, which we can make it as 0 and 1. Okay. Am I audible, students? Hello, students, am I audible?
Yes, ma'am.
Yeah. So what is here? We are going to write it as net, and then net name. Net name is our net name. You have to write it in a double quotation, double quote, inverted comma. So it is, what is net name is D of 0. Okay. So this is our D of 0, right? D of 0. LOC equal to location you are going to assign again in a P, and you will assign it to the input switch. So the pin number is 141 for the input switch. So in the manual, you will observe that there is a manual is available for this pattern 3. So you will come to know which are the different input switches are there with the pin numbers. So we have to assign these pin numbers to these switches. Now what I will do? Now I will just all copy paste this, so we can duplicate it for all the signals. Okay, D of 0, D of 1, D of 2, and D of 3. So D of 0, D of 1. This is your D of 2, and then D of 3. But the pin numbers will be the different. 141 followed by you to choose. Next one is 140. Next one is 139. Next one is 138. Like this, D0, D1, D2, D3 I have assigned now. Now we have to assign a clock signal. So for the clock signal, there is a standard pin is there. So what is it? Net. For the clock, we have chosen the name as CLK. Okay. So we have to choose here as CLK. LOC equal to, what is here, the pin number is P76 or 77. Two clocks are available, global clocks available, and then semicolon. So what is another pin is there available for us? Clock is given load and clear and M. So I will assign now the M selection lines. So net M of 0, LOC equal to. So let I'm going to assign this is also the load signal is also a one switch which is going to make it as either 0 or 1. So for this I will choose this as 137. Okay. So this is 137 and M of 1 will be the 135. Okay. So like this, we have assigned M of 0 and this is M of 1, right? Now what is left is load and clear. Now I will assign load and clear. This is load with LOC equal to pin is previously we assigned 135. This is 133. Again the input switch. And now we will assign a clear signal which is also a input signal. It is also a input signal. Okay, LOC equal to P. We'll assign this as 132. So you have to observe it in a manual and you have to assign. So all the input pins we have assigned as per the port declaration. D, we have assigned clock, load, clear and mode selection. What is left now? Output pins. Now for the output pin, you have to assign this as LEDs. Okay, because LED will act as your output device. So for this LEDs, we have to check in a manual what are the output test pins are there, LED pins are there. Okay, so what I will do now, for this I will just copy this one. So we have to assign 4 bits for the Q. So this is Q of 0 LOC equal to, I have to assign this as your LED pin, which is 161, right? So same thing, Q of 1, Q of 2, Q of 3, right? So you can observe this one as Q of 1, Q of 2 and Q of 3. It is 161. I will choose next pin of LED as 172. This is given in manual. Next one is 156 and the last one is 171. Okay, now I have assigned all the mapping of your pins with the port names I have done, right? So I will save it. So always instead of equal to, we are using concurrent assignment as less than and equal to, right? So everywhere I will just do it as less than and equal to, which is a concurrent assignment of your pins, right? So it is less than and equal to, less than and equal to. Now students, I have completed with this user constraint file. Now I will save it and you can just go here, drop down in a process window. Okay. So here I already synthesized it. Now you can just say implement design. So where it will perform translate, map, place and route operations. So students, this implementation process is done with the translate, map, place and route. Now we have to generate the bit programming file. So click on this generate bit programming file. So this bit programming file you will be able to observe under the folder E drive, wherever the project is saved. So it is already bit programming file is generated. So you can observe this one is universal, that is UNI underscore shift underscore register dot bit file is generated, right? Okay, are you able to see the students this bit programming file? Let me know. Yes, student, are you able to see this bit programming file?
Yes, ma'am.
Okay, so in this way, and you have to download this bit programming file through configure target device. So as I am not connected the device to my PC desktop machine, so we cannot be able to download it. So in this way we have to write the HDL code. You have to simulate it by using the test bench code, and then you have to write the user constraint file. After simulation you have to synthesize your code. We will observe that the mapping of your all the files with the technology schematic, and you can observe the hardware which is generated under the technology schematic. Then followed by you have to write your user constraint file as UCF, in which it will perform translate, map, place and route operation, and you can generate the bit programming file, that is .bit file, and you can download this .bit file onto your FPGA device. Okay, so this is all about your the experiment number 2. If you have any queries, you can ask your queries. Okay, I will stop recording now. Thank you, students.